I want you to picture the day you first learned to drive a car. Really put yourself back in that driver's seat.
Oh, I remember that.
You're gripping the steering wheel so hard, your knuckles are white. You're checking the mirrors every 2 seconds, trying not to hit the curb. It's intense. It takes 100% of your focus.
Oh, absolutely. High stakes, high stress. Your brain is firing on all cylinders just to keep the car moving in a straight line?
Exactly. But here's the question. When you were learning to drive that car, did you suddenly forget how to ride a bike?
Hopefully not. That would be very inconvenient.
Did you forget how to tie your shoes? Or how to cook pasta?
No, because our brains, human brains, are built for what we call continual learning. We stack skills.
Right.
We add new files to the cabinet without, burning the building down.
Yeah.
We can learn to drive without overwriting the neural pathways that tell us how to walk.
But artificial intelligence, generally speaking, it is terrible at this.
It's arguably the single biggest flaw in modern deep learning. In the field, we call it catastrophic forgetting.
Which sounds like a dramatic summer blockbuster movie title, but it's actually a very annoying, very real software bug.
It is.
So today we're doing a deep dive into a paper titled Metalearning Continual Learning Algorithms. And the core promise here is, well, it's fascinating. Instead of humans writing the code to stop an AI from forgetting, what if the AI wrote that code itself?
It's a concept called automated continual learning, or ACL, and it relies on something called self-referential neural networks, essentially giving the AI the ability to rewire its own brain on the fly to protect its memories.
Okay, before we get to the self-rewiring brain, which sounds like sci-fi, we need to understand why the forgetting happens in the first place.
Sure.
If I train an AI to recognize dogs, and then I train it to recognize cats, why does it get amnesia about the dogs? Why can't it just keep both?
It comes down to the optimization strategy. Most AI uses something called stochastic gradient descent, or SGD. Now, think of SGD as an extremely greedy optimizer. Its only goal is to minimize error right now on the specific task right in front of it.
So it's living entirely in the moment, no past, no future, just now.
Completely. When you show it the cat photos, it looks at its internal connections, the weights, and it just changes them to get the right answer for cat. It doesn't care if those specific connections were previously holding the definition of dog.
It just sees them as resources.
Raw resources to be cannibalized for the new task.
It's like building a new house by tearing down the bricks from your old house. I mean, sure, you get a new house, but now you have nowhere to sleep when you visit the old neighborhood.
That's a great analogy. There's a line in the paper from neuroscientist David Eagleman that sums this up perfectly. Enemies of memories are other memories.
Enemies of memories are other memories. That's pretty poetic.
It's the reality of a fixed capacity system. New information is always fighting for physical space in the network. Now, historically, humans, the engineers, have tried to step in and, act as the referee to stop this fighting.
And this is what the paper calls handcrafted solutions, right?
Correct. We try to force the system to remember. One common method is elastic weight consolidation, or EWC.
EWC.
Imagine an engineer looking at the neural network after it learns about dogs and saying, okay, these specific neurons are crucial for remembering dogs, so I'm going to put a digital sticky note on them that says, do not touch.
So you freeze parts of the brain, you just lock them down.
Exactly. You make them rigid. The other common method is replay.
Okay.
This is where the AI keeps a secret hard drive, a replay buffer, full of old data. So every time it learns something new, like cats, it also restudies the old dog photos so it doesn't let those memories fade.
But that feels, well, it feels like cheating. And it sounds incredibly inefficient.
It is.
If a hospital AI needs to remember patient records from 10 years ago to diagnose a disease today, it can't just keep reprocessing terabytes of old data every single night.
It doesn't scale at all.
Yep.
And think about the privacy implications. You don't want an AI on your phone storing a recording of everything you've ever said just so it doesn't forget your accent.
Not at all.
The authors of this paper argue that we shouldn't be hard-coding these rules. We shouldn't be telling the AI what to remember or storing old data. We should be building an architecture that learns how to remember.
Enter automated continual learning. And the mechanism they propose is the self-referential neural network. Now, I need you to visualize this for us. How is this different from the standard networks we usually talk about?
So in a standard network, you have a training phase where the weights change. That's the learning. And then you have a testing phase where the weights are frozen.
Okay.
It's like studying for a test and then taking the test with your book closed. You can't learn during the test.
Okay, that makes sense.
A self-referential network uses what's called a fast wait system. It allows the network to modify its own internal connections while it's running based on the input it's seeing right now.
So it's taking notes during the test?
Even better, it's rewriting its own textbook during the test. It uses a specific mechanism, often a variation of Hebbian learning or the delta learning rule, to do what are called rank 1 updates to its own matrix.
Okay, rank 1 updates is getting a little technical. Let's try a metaphor.
Sure. Think of a standard AI as a sculpture made of clay. To learn, the artist that's gradient descent reshapes the clay. But once the artist leaves, the clay hardens. It's fixed.
And if you want to make it a new shape, you have to smash the old one or get the artist back.
Right. This self-referential AI is more like a sculpture made of intelligent living cells. It has a DNA, that's the meta part, that tells the cells how to rearrange themselves when the environment changes.
Ah, I see.
The slow waits are the DNA, learning the long-term strategy of adaptation. The fast waits are the cells rearranging in real time to store the new memory without killing the old ones.
So the meta in meta-learning isn't just learning big data, it's learning the algorithm for learning.
Precisely. It learns a program encoded in its weights that says, when I see a new task, this is exactly how I should adjust my synapses to store it safely.
It's automating the job of the AI researcher.
In a way, yes. It's discovering its own learning rule.
Now, here's where I get a bit skeptical. If the AI is writing its own rules, why would it choose to remember? We just established that AI is naturally greedy and lazy.
Right.
If I'm a lazy AI, wouldn't I just overwrite the old data because it's easier than doing this whole living sculpture routine?
And that is the critical insight of this paper. They found that you actually have to, well, you have to bully the AI into remembering. You have to force it.
How do you bully a neural network?
It's all about the objective function. Essentially, the scorecard the AI is trying to maximize. They designed an objective with 3 specific pillars. Pillar 1 is immediate learning. Learn the task in front of you. That's the baseline.
Right. If you can't learn the task, you're useless.
Pillar 2 is forward transfer. Use what you learned in the past to help you learn the new thing faster.
If I know Spanish, it helps me learn Italian.
Exactly. Building on prior knowledge. But pillar 3, that's the game changer. Backward transfer.
Which means what exactly?
It means, after you learn Italian, I'm going to test you on Spanish again. Immediately. And if your Spanish has gotten worse, I'm going to penalize you. Heavily.
So it's a threat. Don't you dare forget.
It's a constraint. And the researchers found something really startling. They called in-context catastrophic forgetting. When they trained these super advanced self-referential networks without that specific backward transfer penalty, the models naturally became lazy.
They just overwrote the old memories.
Instantly. The paper has these graphs, figure 2 for anyone reading along, where you can see the backward transfer loss just spike. As the model gets smarter at task B, it actively cannibalizes task A.
Wow.
It turns out remembering isn't a natural state for these networks. It has to be incentivized.
That's almost philosophical. Memory is an active effort, not a passive storage bin. You have to fight to keep it.
And when they applied the ACL objective, that penalty, the model was forced to get creative. It couldn't just overwrite because it would lose points.
So it had to find another way.
It had to find a complex configuration of weights that could hold task A and task B at the same time. It invented a non-destructive learning strategy because it had no other choice.
So let's see how this actually played out. They put this to the test with some experiments. What was the battleground?
The main battleground was split MNIST.
The classic. For those listening who aren't machine learning engineers, MNIST is a database of handwritten digits 0 through 9. And split MNIST means you chop it up. First, you learn to recognize 0 and 1. Then you learn 2 and 3. Then 4 and 5. And you're not allowed to see 0 and 1 ever again.
Right. So they pitted the ACL model against the heavyweights, standard SGD, and the handcrafted methods like EWC, the sticky note method, and replay buffers.
And the standard SGD, how did it do?
Complete failure. After learning the second task, its accuracy on the first task dropped to chance levels, about 20%. It was essentially guessing.
So it learned 2 plus 2, then learned 3 plus 3, and suddenly forgot what a number was.
Pretty much. It wiped the slate clean. But the ACL model, it maintained performance on the old tasks at around 96% in the 2-task settings.
96.
And over 84% in the much harder 5-task settings.
That is a massive gap, 20% to 96%. That's the difference between a failing grade and an A+.
It is. And remember, the key distinction here, and I cannot stress this enough, is that ACL did this without a replay memory.
No hidden hard drive.
No stash of old images. The knowledge was preserved entirely within the structure of the weights themselves. The algorithm itself was the memory.
That is the part that blows my mind. It's like the AI built a memory palace inside its own code, and it just knows not to renovate that specific room.
And it gets even more granular. The paper mentions they used a 4-learning rate version of the self-referential weight matrix.
4 learning rate? That sounds complicated. What does that mean in plain English?
Well, in these networks, you have different components for processing information. You have keys, queries, and values. Think of it like a filing cabinet. The keys are the labels on the folders, the queries are you looking for a label, and the values are the papers inside the folder.
Okay, I'm with you.
The model actually learned to assign different learning rates to these different parts. So it might say, okay, I'm going to update the values, the content inside the folder very quickly, but I'm going to keep the keys, the labels, remarkably stable.
So it learned how to fine-tune its own brain plasticity.
It learned which parts of its brain to keep soft and which to turn to stone.
That's incredible control.
It is.
But we have to play devil's advocate. This is the deep dive, and we don't just hype things up. We have to look at the limitations. Is this thing ready to be a robot surgeon?
Definitely not, no. And the authors are very honest about this. The experiments were mostly on what we call toy data sets.
Okay.
MNISTO, Omniglot. These are small, simple, black and white images. They're low resolution, low complexity.
So it works on the easy stuff.
When they tried to scale it up to split CFAR 100, which involves complex color images of animals, vehicles, objects, things that look more like the real world, the ACL model struggled.
It hit a wall.
It did. There's a benchmark called the 5 datasets test, which is really diverse. And in that arena, ACL was significantly outperformed by methods like L2P, learning to prompt.
Wait, learning to prompt. Why did that one win?
Well, L2P is effectively cheating in a certain sense. It uses a massive pre-trained vision transformer of VIT. This is a model that has already seen millions and millions of images before the test even starts. It has a huge foundation of knowledge to draw from.
So L2P is like a college student taking a 3rd-grade math test.
Exactly. Whereas the ACL model in this paper was trying to learn everything from scratch, pixel by pixel, tabula rasa. It just didn't have the horsepower to handle that level of complexity yet.
There was also a weird quirk mentioned about length generalization. What was that?
Yes, this is a fascinating limitation of current meta learning. If you train the model on sequences of 2 tasks, task A, then task B, it gets really good at handling exactly 2 tasks.
Okay.
But if you suddenly feed it a sequence of 10 tasks,
It falls apart.
it degrades rapidly. It struggles to generalize to a sequence longer than what it practiced on. It's like training a runner for the 100-meter dash. They optimize everything for that exact distance.
Yeah.
If you suddenly force them to run a marathon, they collapse at mile 3.
The model over-optimized for the length of the sequence it was trained on?
Exactly. So it hasn't quite figured out the infinite part of continual learning yet.
So we haven't cracked the code for the robot that lives forever.
Not yet. But the fact that it works at all on the smaller scale, completely autonomously, it's a proof of concept that we shouldn't ignore. It represents a real shift in philosophy.
So let's zoom out. What does this all mean for the listener? We aren't all building neural networks in our garage. Why should we care about this?
It matters because of the future of autonomous agents. Think about that robot butler you're always wishing for.
I am always thinking about a robot butler. I need one.
If you buy a robot, you want it to live with you for 10 years, right? You teach it to load your specific dishwasher. Then 6 months later, you teach it to walk your new dog. Then a year later, you teach it to make your favorite cocktail.
And I don't want it to forget how to handle the dishes just because it learned how to make a margarita.
Right. You don't want it throwing cocktail shakers into the washing machine. And here's the kicker. You can't rely on a replay buffer for a robot that lives for 10 years.
No.
You can't store every video frame that robot has ever seen. It's a privacy nightmare and a storage impossibility.
So for true AI assistants, handcrafted memory is it's a dead end.
It is. You need a system that adapts and stacks skills organically. You need an algorithm that evolves its own learning strategy as it grows. ACL is the blueprint for that kind of system.
And here's where it gets really interesting for me. The paper drops a provocative thought at the end, connecting this to the AI we're all using today, large language models like GPT-4.
Yes, the LLM connection. This is the part that keeps me up at night.
We know models like GPT-4 are trained on, well, essentially the entire internet.
Hmm.
That's one massive, chaotic sequence of tasks. Python code, then French poetry, then a recipe for sourdough, then a history of Rome.
It's the ultimate sequential learning task.
And the authors suggest that LLMs might effectively be doing ACL accidentally.
Think about it. The objective of an LLM is to predict the next word. But to predict the next word correctly across that much diversity gigabytes of diverse topics, the model has to figure out how not to overwrite its knowledge of French grammar when it's learning Python code.
Because if it forgets the French, it fails the prediction when a French website pops up later in the stream.
Exactly. So the backward transfer penalty, that threat of failure we talked about, is implicit in the sheer scale of the data itself.
That is a wild thought. We're here in the lab trying to invent the wheel, trying to mathematically prove how to make AI remember, and the big models might have already evolved these structures in the wild just to survive the training process.
It suggests that learning to learn might be an emergent property of scale. If you make the task hard enough and the sequence long enough, the brain synthetic or biological, it finds a way to structure itself to survive.
It's convergent evolution. The AI arrived at the same solution our brains did just by taking a different path.
It's a distinct possibility.
So as we wrap up, I want to leave our listeners with a thought on that backward transfer concept. We talked about how the AI is forced to use the new thing to reinforce the old thing, or at least not break it.
Right. It's the ideal way to learn.
So think about your own learning this week. What did you learn today that changed how you view something you learned yesterday? Did you overwrite the memory? Did you just delete the old file? Or did you upgrade it?
That's the human version of ACL. We're always rewriting our own code.
Are you doing your own backward transfer, or are you just catastrophically forgetting something to mull over? Thanks for diving deep with us.
See you next time.